Hello, in this video I wanted to introduce you to some of the different kinds of telescopes that astronomers use to look at space and the different variety of things that are there for looking at different wavelengths. So first I wanted to show just kind of a really sketch of how telescopes work and actually even how the eye works. Um, but even if the telescope itself is more complicated, generally you can think of it as having two main pieces, a large objective lens, which its main purpose is to be really large and to collect a lot of light and to start focusing it and bringing it into one place. And then you have some additional optics, usually an eyepiece that helps focus the rays and create something you can see. And this illustration I just wanted to show because it shows how when you are looking through a telescope with your own eye provides one of the lenses that is part of the system. And you can think of the retina on the back of your eye as taking the place of an actual camera sensor. But if you're using a telescope with a camera, it's much the same process where you want to focus those rays and form an image on the camera, but the camera itself has the optics that normally would be in our eye. Um, what that means in practice is that if you're looking through a telescope versus taking a picture with a camera, there may be a difference in the kind of eyepiece that you might want to use because for the camera you want one sort of eyepiece, but since we have lenses in our own eye that do some work themselves, we don't necessarily need that. But the main thing is that telescopes generally consist of at least two optical elements, often many more than that, to try to minimize errors or just deal with other issues that might show up. But a lot of times they're described as effectively being composed of two main pieces, sort of a big objective which collects all the light and something else that essentially focuses it and makes a good image. And so they might be lenses, they might be mirrors, but they essentially all serve the same purpose. And so let me show you a few slides just of all the different kinds of telescopes. Not even all of them, but some of them. So unfortunately, this one is not around anymore. You might have heard of this in the news. This is Arecibo telescope in Puerto Rico. It unfortunately was very old. It's been around for quite a while. It's been on a lot of movies and stuff because it's got pretty cool looking to it. But I wanted to put a picture of it because you can kind of, even from this picture, see a little bit about how it works. But the important thing about this telescope is it's a radio telescope. This isn't an optical telescope. You can see it's not shiny. It's not reflecting visible light. And in fact, if you look closely at it, at a better image, you can see it's not even really completely solid. It's made of metal, but it's actually a mesh to let the rainwater go through so you don't wind up with a big pool. But radio waves have a pretty long wavelength, and so they're not really sensitive to little holes like that. As far as the radio waves are concerned, this is a mirror. This big thing in the center forms a mirror. That's what you might call the objective there, and then it actually takes the light and bounces it back upwards towards this little dome that you see suspended from cables up above, and that's in this case it would be called a secondary. That's what kind of focuses the light, and all the instrumentation for actually detecting the radio waves is actually up here. And then that information is carried through some wires back to the main operating building for the telescope. But you can see that one of the advantages of a telescope like this is since it's radio waves with relatively long wavelength, you don't have to have real precisely engineered mirrors or anything, so you can make it very large. You can see these are cars here down in the parking lot for size comparison. The disadvantage, of course, is you've got this big mirror here. You can't move this. You can't change what direction it points. What they have to do with a telescope like this is wait as the Earth rotates. Different objects will sort of appear in the sky above it through the course of a day. You do have some ability to change where you're looking by moving. Actually, what they can do with these cables up here is they can move the secondary. So if they move it off to one side, it'll sort of see light reflected from the opposite direction. So you do get a little bit of control to sort of steer which reflections you're looking at from which part of the sky. But you're mostly just looking at things that are close to straight up above. On the other hand, it's a huge telescope, which means you get to see very faint things. And so this was in operation for a long time and did a lot of neat stuff. And unfortunately, basically due to lack of funding, eventually just collapsed about a year or two ago. I don't remember exactly when. Um, but there are other telescopes like that in the world, and so it's unfortunate that it happened. But I wanted to show there's also this one. This is the FAST. It's called the FAST telescope. This is actually built in China, way out in the mountains to get away from local radio noise pollution, basically. Because if there's radio stations, it's a radio telescope. So if there's radio stations nearby, it kind of creates some noise pollution. So this is even larger. It's hard to get a sense of scale for this one because I don't really see any buildings nearby in the image. But this is also very large, and I don't think you can see the secondary in this image. I'm not sure if it had been built yet when they took this image. But this is a very big radio telescope, and it's similar idea. You can't point this thing. You have some limited ability, but it's very large and can see very, very faint objects. And so that's one example of a very special kind of radio telescope. And there are lots of other kinds of radio telescopes that are smaller, more steerable, but these are sort of the most extreme examples. This is actually a different wavelength sort of radio telescope. This is part of the Square Kilometer Array Observatory. The idea here is actually each of these metal things on a stand here is actually about the size of a person, roughly. It's hard to get a sense of scale from this image, but they're not that big. They're basically like antenna, and they're for a somewhat different wavelength of radio waves, but here the idea is to just make lots of these and spread them out over a huge area. So just literally hundreds or thousands of these things spread out the desert. I think in this case, this is the Australian desert. You just find a lot of wide open space and put large arrays of these things out. And you can also do some interesting science with that. And so this is in the process of being built. They've built sort of smaller scale versions of it to kind of test out all the technology, make sure all the kinks are worked out. But that's another example of just, it doesn't look at all like what we do normally imagine a telescope being, but it is a radio telescope. And it actually can, this particular telescope is aimed at sort of looking very back far away early on in the universe and detecting radio waves from galaxies and other things quite distant from us. And so that's another interesting, more recent development. This is a video of, I'll play it in a second. This is a video from early on in the project, and I'll show you a picture from later on in the project. This is a more traditional telescope, but this is now called the Rubin Observatory after Vera Rubin, an astronomer who was instrumental in developing the idea of dark matter. And this is a concept video where here, this is just all computer animated, but it shows you a bit of the design of the telescope. In fact, it was originally called LSST, Large Synoptic Survey Telescope. But this was a telescope, or is a telescope, or will be a telescope designed. You can see the design. It's pretty big around. There's a person there for scale, but it's also very compact for such a large telescope. You can see as I play here, that's shiny thing in the back, that's the primary mirror, and then the secondary, and there's actually multiple mirrors sort of right in front, but it's all rather compactly designed. Because one of the main goals of this telescope is they wanted to actually have a large field of view, and they also want to be able to take lots of images over the course of a single night of as much of the sky as they can see. So it's constantly taking moving around and taking exposures of different areas of the sky. And so to make that easier, you don't want to have a big long thing that wobbles a lot when you swing it around. You want a nice compact thing so that it's relatively easy to move. So the other thing unique to this telescope, and let me skip this. Here we go. This is the camera. This is the digital camera at the heart of this telescope. Again, there's a person here for size. This is just the sensor chip of the camera. It's many thousands of pixels across by another many thousands of pixels. It's the largest digital camera I think ever made. And these green, purple, yellow, red, those are filters. Those are basically filters on a mechanized table that can be rotated and put in front of the camera to select specific colors of light. But it's just this really big camera. You can see there's an animation of what it looks like to slide a filter Actually, the light winds up coming up from the bottom from this view. So, and here they sort of slide the whole thing together. This is basically just the camera and then some optics to correct, do some image correcting before you get to the camera. And then here they show sort of a cutaway of what the thing looks like as you put it together. But again, whoops, let me go back. Sorry, I clicked on the wrong. Let me go back to this point and stop there. This is sort of with all the support structure cut away, so you can just see the actual telescope. There's that camera in the middle. This big thing at the bottom is the primary. Actually, the outer part is the primary. What happens is the light comes in from above, bounces off the primary mirror. This shiny up thing here is a secondary mirror. It hits that next. Then the light actually bounces down onto this inner part down here. This is actually a tertiary mirror, a third mirror, and then it goes into the optics and into the camera. But this bouncing back and forth, that's one way of making the telescope very compact. And that's not unusual, actually, even in much smaller cameras today. If we get a chance to go on the roof and do some observing, even the telescopes that we have up there, they're not nearly as complicated as this or as big, but they do some bouncing back and forth to make them more compact and easier to use. And so that's a common trick, but in this case, they've taken it to an extreme. And so here's another image of sort of putting the whole thing together and then just putting the whole thing in a dome. This is now, don't need to look at, so that was produced, 10 years ago. This was in the design stages and just started being built over 10 years ago. This is a much more recent picture. This is an actual photograph. They're still working on it. The actual telescope itself is not fully installed at this point. And you can see this is an actual photograph of the building. They've now got a site in the Andes, on sort of this plateau on the top of the Andes Mountains in South America. And you can see there's some construction vehicles and some trucks and stuff, but it's in progress, and is actually getting close to completion. And so that will be another new exciting telescope that being developed. One of the reasons you want to cover so much of the sky each night is to look for objects that change from night to night. So and one example of that might be supernova. Those are things stars that explode at the end of their life. We'll talk about those, but one day you don't see anything, and then the next day maybe you see a bright light, and that's a supernova starting to. Some of the big ones might be bright for a couple weeks, but if they're fainter, you might only see them for a few days. Those are very distant objects, but you can also find meteors in our own solar system, asteroids, actually, I should say, in our own solar systems that also move from night to night. And so this turns out to be a good way to find them. So there's just multiple science goals that can be achieved by having this sort of ability to scan the whole sky every night. So that's another type of telescope, a more traditional optical telescope. This is a telescope that we'll see some images from at some point, because this was actually an X-ray telescope. This was a satellite telescope, because we can't really, fortunately for us, most X-rays don't really get through the atmosphere. They get absorbed. So if you want to see them, you've got to go out into space. You can't really see the insides of the telescope here. But X-rays also tend to go through most things you might try to use as mirrors. So what you actually have to do is you have to use special rings of metal to sort of very gently deflect the X-rays just a little bit to try to focus them and make an image. So that's why it's so long, actually, is because the X-rays come in pretty much straight in one end, and then just very gradually get bent by these series of rings, and before they can get focused onto something that can make an image out of them. And so all the camera sort of X-ray camera electronic stuff is at the back end here. And then the rest of this is just sort of control systems, solar panels to power the whole thing, some thrusters to make sure the telescope stays pointed at where you want it to stay pointed, a sunshade to keep things from getting too warm in the sunlight, and so on. But this was an X-ray telescope that produced a lot of really important images of what things look like in X-rays. And so I also wanted to show, this is or rather I should say newly producing results. This has been a project that's been decades in the making, but this is in many ways a very, very different kind of telescope. This is actually an observatory that doesn't actually look at light. This is actually a gravitational wave observatory. It looks at ripples in space itself um, that are due. Well, we'll talk about where they come from in a second. But if there are these ripples in space, as these sort of gravitational waves pass through this, the actual observatory is sort of the central building, and then these two arms. There's one arm here that goes up, and then one arm goes off to the left. And what it does is it sends laser beams down each arm, and it's able to very, 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 very precisely measure the distance along each of these directions. And what happens when a tiny little distortion of space comes passing through uh, the Earth and so on, it's certainly nothing that we can notice. But what happens is it stretches. It might stretch one of these distances just a tiny, tiny little bit, and then compress maybe the other at the same time. And so you'll notice this tiny, 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 tiny change in distance. A change in distance much actually smaller than a single atom, but they're actually able to measure it. And so they look for signals like that. And actually, building one of these, if you saw signals, people would always question, well, maybe it's just noise. How do you know that it really came from a gravitational wave? So that's actually why they built two of these. This is one I think this is the one in Louisiana. There's also one in the state of Washington. I, um, and so what they actually do is they run both of these at the same time. And the idea is if they see the same signal at about the same time in both observatories, then they're more confident that it's an actual astronomical signal from space rather than just some local little micro earthquake or something, because that turns out to be something else that happens all the time and causes little distance fluctuations. So this has been in the planning stages since decades ago. I don't even remember the beginning of it, and it's been built and operational for a while, and they've just been getting better and better at controlling all their signals and their noise. And then now, in the past few years, have been publishing observations of gravitational waves. And where do gravitational waves come from? You get these ripples in space itself when you have very massive objects sort of spinning around very quickly, especially when they're not completely spherically symmetric. So, for example, if you have two black holes that are sort of spiraling in towards each other and eventually merging, that creates a lot of ripples in space, and those travel outwards as gravitational waves. And so this thing actually detects the signals from merging black holes, and they've actually detected several by now. They also can see merging neutron stars, which are dense but not quite black holes, but just these very exotic things. And so it's different from an optical telescope in the sense that it's almost more like a hearing than seeing things. It sort of detects these signals from just about any direction they come from. You get some information about what direction they come from, but not maybe real detailed information. Because even if the gravitational wave comes in from the side or whatever, you still see these changes in the distances. But they're able to use the fact that they have multiple of these across the world, and now there's more than just the two. There's one in Italy that also provides supporting data, and there's one in Japan that's being brought online, and there's plans to build just more of these to help combine all the signals from all of them and just get more refinement of where these signals are coming from, get better sense of where they are and how far away they might be. I wanted to show a few more slides of what this thing looks like on the inside. So since they're shining these laser beams down each pathway, this is the mirror, very precisely manufactured mirror, very fancy, suspended so that it doesn't vibrate whenever there's ground vibrations, which it turns out there's tiny ground vibrations all the time, so they have to deal with that. But this is sort of the technology, and again, it's hard to get a sense of scale for this thing, but this is about this is several feet high. This is maybe not quite as big as a person, this whole image, but it's a decent sized thing. And they just shine a very super bright laser down at this mirror when it's in operation through a vacuum. The whole line has all the air pumped out, and they use that to measure the distances. You also want to measure, there's the control room, and actually this is one, I think they were seeing some of their first signals. So they just have a control room. I kind of like this picture because it just In a lot of ways, the technology is so exotic and weird, and this is a new type of instrument that's never been done before. Like this is really the first observatory that's directly measured gravitational waves like this. And but the control room doesn't look particularly like anything out of science fiction. Some of the equipment does, but this is the control room. It looks like an office. They have pretty normal office furniture. They have some screens. They have a lot of monitors up on the wall, but um, everybody's just very seriously looking at the monitors. And so I like that image. So that's just the quick summary I wanted to give. There's lots of other types of telescopes. I'll show you some examples back when we're in person and looking at some things, but I wanted to just remind everyone at the end of this that we do have some homework for next Tuesday. Just look at chapter 7 on light. Look at this specifically at question 12 and then maybe 3 others. And also just reinvent and refine your proposal idea up to about a page with 2 references. Don't forget about that. And we'll use that as the jumping off point for then kind of thinking about how we can combine our efforts and move on to the next stage of the proposal. All right, thanks.